So I'm starting this video over because I probably said something I shouldn't have said. I was calling out a kid for not watching the videos. I wasn't very nice about it. But anyways, these are your notes for 12.5 actually, that needs to be edited. Probability distributions. And I usually throw some of this stuff out, but I've had a number of kids who think probability can exceed 100%. It's way more than usual. So we're just going to create a small probability distribution table for flipping quarter 10 times. And we'll just make a table. Tables are boring, but they're always right. Let's see here. Heads and tails, X, and the probability of event X happening. So you flip a coin 10 times, and you get tails 7 times, and you get heads 3 times. The probability of getting heads 3 times would be 3 in 10, or 0.3, okay? Getting tails would be 7 in 10, or 0.7. Now let's do a total line here. 3 plus 7 is 10. 0.3 plus 0.7 is 1. Probability distributions have to add to 1. If I have a string of things that I'm talking about, the probabilities add to 1. It's just the way it is. Determine whether each distribution is a probability distribution. And by the way, let's go over probability again for those kids and hope that they're watching. Probability is stuck between 0 and 1. It is not negative. It cannot exceed 1. It is a number stuck between 0 and 1. Now a distribution of events would have to add to 1. A fifth plus a fifth plus a fifth plus a fifth plus a fifth is 1. This one is good. Example B has that. Probability cannot be negative. This is a big fat no. That is not a probability distribution. Even if the numbers were to add to 1, it is impossible. All right? So what we got here? We got a quarter. We got an eighth. Let's just make these all the same. A quarter is going to be 4/16, an eighth is going to be 2/16. And let's see if this is true. 4 plus 2 is 6, plus 1 is 7, plus 9. It equals 6/16, which is 1. This is a good distribution. That one got a check. That one got a check. Let's check this one. If I do 0.5 plus 0.3 plus 0.4, I get 1.2. This is not a distribution, because this is saying that the probability of all these events together exceeds 1, and that's not true. All right, I've talked about that. Here's a concept called a binomial experiment. A binomial experiment is an experiment that consists of a fixed number of trials with the following features. And the truth is, it's either an experiment that involves success or failure. So each trial has 2 possible outcomes, one of which is success. The trials are independent of each other, which means if I do something once, it doesn't affect the outcome the second time, and the probability of success is the same for every trial. And notice that's what they talk about. A probability experiment has 2 outcomes. There are 2 outcomes. You succeed or you fail. That's it. 2 outcomes. You succeed or fail. If that's true, you get to use what's called a binomial experiment. Binomial, your generation knows what that means. All right, so is this experiment a binomial experiment? The spinner has spun 3 times. Assume the spinner is equally likely to stop in any of the sections. Success is landing on a section marked go forward 2 spaces. Yes, this is a binomial, all right? Each trial is independent of each other. That's probably not the best wording. Success is clear. You either succeed or you don't. There's no in-between ground. And the probability of going forward 2 spaces is going to be the same each and every single time. It's not like we introduce something new, but the probability of forward 2 is always equal to, let's see, we have 1, 2 of what? 8? 2 and 8, or 1 and 4? So this is definitely a binomial experiment. Definitely a binomial experiment. All right, is this experiment a binomial? In a class of 23 students, 7 students completed the term project. 2 students selected at random must give presentations. Success is that the student has completed the project. No, it is not. Why is it not? Okay, no. The reason is going to be is because what happens? If we pick a student and say the first one, the first try, the probability of success is going to be 7 in 23. Okay? The second try, we've got some choices here. It could be 7 in 22, or it could be 6 in 22. Because maybe we picked somebody that did a project and we had to decrease that, or maybe the first try we picked somebody, we didn't get success, okay? So what has happened here is the probability of the event has changed. And if you go back and look at what it says about binomial experiments, the probability of success is the same for every single trial, okay? So the only way this one could have been true if we put the student back in the pool to select from. And why would we do that? We would not do that. They've already done their job, they've already gotten their 0 or their passing grade. All right, is the experiment a binomial experiment? If so, find the probability of success. Explain. You select one card at random from a set of 7 cards, 4 labeled A, 3 labeled B, then you select another card at random from the cards that remain. For each selection, success is that the card is labeled A. This is not a binomial experiment. Why? We did not replace the card. If it had said the card is replaced, meaning put back into the deck, it would have been binomial. Because for the same reasons the last one was not binomial, if you pull a card, you change future probabilities. You become what we call conditional probability. All right, you roll a standard number cube 4 times. Assume that each time you roll the number cube, each number is equally likely to come up. For each roll, success is getting an even number. This one is binomial. It's got everything you need. Okay? We have an equal chance of success every time we roll. We're not changing probabilities. You're always, it's 4 cube. It's a standard number cube. 6 sides probably, all right? So you always got a 1 in 6 chance. A standard number cube should be a die. So the probability of getting an even or success, which is success, is always going to be 1 in 2. A standard number cube is going to be 1 through 6, all right? Every time. Definitely binomial. Definitely. Here we have a nice little formula. I'll be honest with you, I didn't even remember it. It's been so long since I've used it because I don't use it. I use a calculator because the calculator has it. And we'll go through this, but I'm not too terribly concerned that you know this particular formula. I doubt that I would actually assess you being able to do it by hand, but we're going to do it in the notes. So the binomial experiment is the number of ways to get R successes in trials, that's an NCR, times the probability of those successes times the probability of the failures. All right. A grocery store gives away scratch-off cards with the purchase of more than $100. Terrell has 5 scratch-off cards. What is the probability that he has exactly 3 winning cards if each card has a 30% chance of being a winner? Now, if you have a 30% chance of being a winner, you wouldn't understand this if you're a loser, but you have a 70% chance of losing, of being a loser as well. Okay? Is this a binomial experiment? Yes. Scratching off one card does not influence the next. It is binomial in nature. So, the probability of this event here, we have 5 scratch-off cards. We want to see if we have 3. So the probability of 3 successes is going to be 5 choose 3 times P, which is the probability of success. This is P, okay? We're going to use the decimal form. We always do when we do some actual math. To the R. R was 3. Remember, this is N, this is R. Times 1 minus P, so 1 minus 0.3, which we've already figured out, raised to the N minus R, 5 minus 3. It's just feed a formula, kids. 5 choose 3 is something that if you understood the formula for combinations, you could probably do in your head. It's 5 times 4 times 3 times 2 times 1. And that's sitting over 3 times 2 times 1 times 2 times 1. Gone, gone. 5 times 4 is 20, 10. This is 10. You can also push buttons if you want to. All right, it's up to you. 0.3 cubed? Yeah, even I don't want to do that in my head. 0.0027? I feel like it's 0.0027. It ought to be. Yeah, 0.027. And this would be times 0.7 to the second, which is 0.49. And I'm not trying to waste your time here. I'm just saying, most people don't realize is that you can actually do things by hand if you want to. And I did some of it. So this is what I get. I get 0.1323. Now, if that's too much for you, we're just going to check my math here, make sure I'm still functioning right. We had a 5, choose 3. Hopefully you can hear me over the class next door. And then we had, in parentheses, a 0.3 to the third. And if you don't know what 1 minus 0.3 is in a calculator, or without a calculator, the calculator shall not judge you. And if you don't know what 5 minus 3 is, the calculator won't judge you either. 0.1323. That is the probability of 3 successes. So this is the probability of exactly 3 winning cards. Oh, by the way, this guy down here, this is the probability of a loser. All right, moving forward. To the nearest 1/10 of a percent, what is the probability that Terrell has more than 3 winning cards? More. This would mean that he has 4 or 5. And notice the word 4. He has 4 or 5. So I'm looking for the probability of 4 successes plus the probability of 5 successes. So we're going to have to do a 5C4. It's still 0.3 to the 4th power. This is 1 minus 0.3, and it went N minus R, 5 minus 4. Here it's going to be 5 choose 5 times 0.3 to the 5th, 1 minus 0.3, and then this is going to be 5 minus 5. It's just a formula. And I'm about to show you an even quicker way, okay? These things can be done quicker than this. It's been a long time since I've done it in a calculator, but this isn't too bad. But the key word here was, when I thought about it, 4 or 5. He has more than 3. All right, so I'm going to go up to some previous work to save myself some time here. I'll just change things. .02835. Okay. Pay attention to what I'm doing in a calculator. 0.01215. And we have the add sign. .0405. All right, let's see here if I can remember something here. Let's see here. Second bars. Nope, not that one. Stat. That's not it. It's under second bars. Second bars. I'm looking for something called binomial. There it is. There's two choices here. You got binomial probability distribution formula and you have binomial cumulative density formula. All right. The cumulative density formula should be for above, but it's no, I think it's for below. I don't want to teach the cumulative density formula. Not until I've played with it a while, because it's been a while. So second bars, let's just do binomial probability distribution formula. So we had 5 trials. The probability of success is 0.3. I had a 4, right? Paste. There's that number from earlier. Add to it the same thing, but this time we had 5 trials. 0.03. Apparently I did something wrong here. Why don't those match? Okay, apparently when I push buttons over here, I got something wrong. I'm not sure what happened here. Let's go back up to that. Sorry I'm wasting your time. Bothers me. Oh, I see it. You probably already caught me. I'm kind of glad I went back over the calculator here. Okay, that's it. See how they match now? But anyways, I can take that guy and I can add that result in 0.0308. So the function binom PDF, which is definitely worth talking about here, but you have binom PDF. It's under second bars. We've been there before. And then you just scroll. All right? That's all you do. You just scroll to it. But you had to realize here that it was 2 or more things. All right, so let's see here. Here's a do you understand? I don't know if I want to do that one. That probably needs to be thrown out. Let's do something else here. Let's make up a question real quick. And let's just do something simple here. Let's do about a multiple choice test. So, a test is made of 20 true, false questions. Let's just make up a name. Chris could care less if he passed. He randomly writes TF. Okay? Is this a binomial experiment? Yes. All right? What he wrote on the for one question didn't affect the other. All right? It's binomial. The probability of success, which means you get a question right, is always 1 in 2 or 0.5. It's either true or it's false. It's right or it's wrong. Let's do some questions here. What is the probability he gets 5 right? All right? We can do that with binom CDF. So second, VARS, binom CDF. And we have 5 right, so 5 trials. Probability of success is 0.3. Sorry, the number of trials here is how many questions you have. It's 20. 20 trials. Probability of success is 0.5. And we're hoping that he gets 5 right. 0.0148, okay? 0.0148. Let me snipe that. I got a class coming in, so I'm gonna pause this real quick. And hopefully I'll get back to it. Maybe during my lunch break, because you know that's how I am. I just work, work, work. All right, let's pause this video.